So let's see how this works.
Today I'm going to use a rotary encoder to control a motor and talk about rotary encoders.
So the way a rotary encoder works is basically the little wheel that spins on the mouse in either direction. So it controls a little tiny metallic disc, and that disc is connected to the common pin, which is C, and that is usually connected to ground. And what happens is you have these two other little metal contacts in these windows in the disc. And so as the disc spins, it makes contact with either A or B or both, and that conducts through there between these various pins to C. So it gives them a common conductor. So when this spins clockwise, it makes contact with the A pin first, and then it makes contact with the B pin. And then as it's making contact, so it was contacting both of them at one point, and then as this window rolls in, the A pin goes off and the B pin goes off. And so if it's spinning counterclockwise, so it makes contact with the B pin first, so that conducts first, then A, and then both go off. B goes off first and then A goes off. So here's a representation of that graphically. So if you're spinning clockwise, let's go with clockwise first. The A pin goes on first, followed by the B pin, and so on and so forth. So if you're going to represent these in a binary fashion, with A being the first, the most significant bit, and B being the least significant bit here, there would be 0, 0, then 1, 0, 1, 1, 0, 1, and 0, 0 when they're both off again. Similarly, in the counterclockwise direction, B goes on first, right? As it's spinning counterclockwise, B makes contact with this before A does. And so B always goes on before A and goes off before A. So that way, if we use B as our clock, or as our clocking signal, and A as the data signal, what happens is when you're spinning counterclockwise, B goes on. Every time B goes on, A is off. So at the rising edge of the clock, A is always 0. And so that way, that tells you that your data is 0, and whatever flip-flop you put this information into, it's always going to be 0 when it's spinning counterclockwise on the Q output. And on the clockwise output, A is always on when B goes on. So at the rising edge of B, A is always positive. So that Q output on the flip-flop will stay on. So here is the circuit that I designed there. And so I have here A, B, and C. C is connected to ground. I have two 10 nanofarad capacitors connected between A and B and ground. And basically these are just debouncing for the switch contacts. I have 10K resistors going to 5 volts to A and to B. And my indicator lights are basically just driven by transistor-based drivers. I have a 100K resistor here, and through an NPN transistor, and LED light that goes to ground. So that indicates when A is making contact, or B or both are making contact. And so the outputs of these, I said to use B as the clock. So here I have the CD4013 flip-flop. It's a D flip-flop, and basically the B signal is serving as the clock input, and the A signal is serving as the data. And so I have the set and reset portions of this D flip-flop set to ground. And then, so the output, I have Q and Q bar, and Q is the output when the D is high, and then it's clocked in at high, and that indicates that it's going clockwise. And it always goes off when it's going counterclockwise. So that's the way that circuit works. So today I'm going to show you guys this rotary encoder. I made this before, but now I finally found something that I'm going to put it to use for. And so this is basically a rotary encoder from a mouse. It's the little wheel inside a mouse, and what it does is it spins in either direction, and it gives you a signal. And so the signal, based on the contacts, so there's 3 different contacts. There's a ground pin, which is the yellow wire, and an A and a B pin. And as you spin it, it makes contacts at different times. And so I have this little circuit set up. It looks a little complicated here, but I'll basically explain it. And using the oscilloscope also. So the yellow curve is the B, so the B pin is the green and the A pin is the blue. And so I have these set up so that as you spin this in either direction, these pins make various contacts, grounding the circuit and turning on the current in different directions. So as I spin it clockwise, what I'm calling the A pin, which is the right-sided light, it goes on first and then it turns off first. So I'm spinning it slowly now here. A goes on, then B goes on, then A goes off, then B goes off. And it continues that way the more you spin it. So now let's show this on the oscilloscope. So now both pins are off, and so the blue curve is the A pin right here. And as I spin it once, that goes on. And the yellow curve is still on the 0 volt line, at logic low. And then as I turn it a little bit more, you should see that go on. And now both are positive. And then as I turn it more clockwise, the B, which is the blue curve, once again should go off. And then the A pin goes off. And so I have the lights showing it, so I don't always have to have an oscilloscope. So they're just indicator lights. So now, if you spin it counterclockwise, the opposite happens. So let's get it to the point where the pins are both off. And so as I spin it counterclockwise, B goes on first, then A goes on first, which is the opposite. And then B should go off first, and then A goes off. So using this logic, what I've done here is I've connected this to a D flip-flop. This is basically powered off of a 5 volt through a voltage regulator here. It's a 5 volt circuit, and this is a CD4013, which is a pair of D flip-flops. And the way I have it is the output from the A pin, which is the blue pin, which is the blue curve, goes to the clock input of the D flip-flop, and I'm sorry, that goes to the data pin of the D flip-flop. So this yellow wire here, that is the going to the data pin, and the clock pin is controlled by the B pin. So what I accomplish with that, so let's say I'm turning this clockwise, A goes on first, right? So if A goes on first, let me get it to A, just A is lit up, it's very sensitive. So A is lit up here, and So if A is lit up, that's the data. That's a 1, a logic level 1, or a logic level high, 5 volts here. And so if I have B as the clock pin, the rising edge of the clock will trigger the flip-flop to go on, to flip to the set mode when the data level is high. And so since the data level is high, which is the A pin, the B pin is the clock, and when I turn it clockwise again, that triggers it to set. And so what happens is the Q output, which is that light on the left there, means that it goes on and it stays on. And so no matter how much I turn this, it stays on. Now, using that same logic, if I'm turning this counterclockwise now, so counterclockwise mode, the B pin goes on first. That's the clock, rising edge. So that rising edge of that clock went on while the logic level of the data pin, which is the A, on the right, the light on the right, is low. And so that triggers the D flip-flop for the Q bar, the inverted Q output, to be high, and for the Q output to be low. And so no matter how much I turn it counterclockwise, it's going, and I'm going to keep turning it, it's going to stay in that direction. Now, so if I turn it clockwise, that Q goes on, counterclockwise, Q goes off, clockwise, counterclockwise, clockwise, counterclockwise. So in this fashion, I could use this to control an up-down counter, where the output of this D flip-flop will be, the Q of the flip-flop will be connected to the up-down toggle of the binary counter, and the clock of it will be this A pin right here, which will be the data point. And so this way I'll be able to use a counter and control the counter direction just by using this rotary encoder. I'm going to show the schematic for this too. And once again, the clockwise mode, the counterclockwise mode, I'm going to show on the oscilloscope. So as the clock pin, which is the B pin, which is the left LED light, goes on first while the A pin light goes off. So I'll show you that here. This is turning counterclockwise, and see, that's off, and you can see the logic levels on the oscilloscope. And then finally it turns on, and it keeps on turning in that direction. And in this way, using this logic, you can get this rotary encoder to not only count or do activate something going in a particular direction. I'm going to use this in an analog fashion. Obviously, I'm not plugging this into any microcontrollers or coding or anything like that. That's not my style. So let's see what we can do with this. An example of an application for that rotary encoder in the real world, just to play around. I hooked up the H bridge of a motor controller to the output of the D flip-flop from the road that's controlled by the rotary encoder. And so basically the Q from the D flip-flop is here and the Q bar is here, and basically it's a quick and dirty little transistor based H bridge. And so you hook up the motor here, and your supply for the power supply for the motor is whatever voltage you're using, or the PWM controller input, whatever it is, goes in here, and the ground of it goes here. And so what happens is when you flip the motor controller to clockwise position, you want the motor to spin clockwise, the Q will go on and the Q bar output will go off. And so this provides a logic 0 here and a logic 1 here. A logic 0 at a PNP transistor will open up that transistor, and a logic 1 on a PNP transistor will turn this one off, and a logic 1 here will turn this one on. And so the flow of the current will go like an H bridge, and it will rotate clockwise. Similarly, if you turn the rotary encoder counterclockwise, the Q bar will go on and the Q will go off. And so in a similar fashion, this will go on, and so this will be this switch will be open, this switch will be on or closed, and this switch will be, since this is off, this switch will be off and this switch will be on, and the flow of the current will go in this direction and spinning the motor counterclockwise. So that's just how that works. So this is an H-bridge circuit. It basically has two PNP transistors at the top there, getting power from the red wire in between them to their emitters. And then the other two are NPN transistors going to ground. And so the bases of the transistors are getting signals from these 1K potentiometers. Instead of going to ground, it's going to the MOSFET there in the background. And that MOSFET is getting its gating signal from the previously built PWM generator, and the output is going to ground. And in this way, I'm controlling the motors with this from a mouse, basically a rotary encoder. The way the rotary encoder works, if I turn the power on, is it's giving you an output of 0, and I have the lights from it, and you can see the motor on a very low setting, so it's getting controlled slowly. And if I turn the wheel of this to the clockwise, it spins clockwise. And if I turn it counterclockwise, it goes counterclockwise. And in that way,